Thank you so much for having me. My name is Sreeniketh Vogoti. I'm a graduate student at the University of Washington. My talk today is entitled Formalizing Graphetics through a Grapheme-to-String Generative Grammar. That's the fancy title. The pithier, more provocative title is Towards an IPA for Writing Systems, question mark, possibly. So let me introduce a scenario to you. Imagine that you and the person next to you are imprisoned in 2 rooms, and your only method of communication is a standard keyboard. You're given a writing system that's unknown to either of you, and you have to teach the other person its graphemes without being able to show it to them visually. The other linguist must be able to transcribe the writing system from the instructions given, and presumably there's a judge validating that what you transcribed is indeed accurate. The other person is transcribed. Before they're separated, they're allowed to agree upon some common rule set or annotational system for communicating these graphemes. If they succeed, they live. If they fail, they die. We want to have stakes. What rule set should they agree upon? Is there such a rule set? Can we do this? So there is a rule set that you can do that's very simple. You use it every day. It's called pictures. So the naive solution is that you represent each grapheme as a series of cells in some grid. And you say white is 1, black is 0, or the other way around. And then you annotate it like this. Each row is 1 row of the image, separate it with a space, next row, next row, next row, next row. This is maximally descriptive. You have all the information that you need to reconstruct any grapheme of arbitrary size, any image, anything that you want. The disadvantage is that it's too specific. It overconstrains the definition of grapheme, such that if you tweak even 1 pixel, it's a completely different thing. It would be like representing the phoneme P with a spectrogram recording of the letter P instead of some IPA or some more common system of abstraction. So we want to capture all meaningful variation in the grapheme without overgenerating, basically. So you could have many possible images that would be ridiculous if they were graphemes in an actual script. You could have the Mona Lisa in grayscale, but that wouldn't be a grapheme. So you want some constraining abstraction. There have been a lot of previous approaches to something resembling this system. So my favorite is the planar grammar and the ideographic description sequences for Chinese. So there is a function that says, here's what you concatenate. And this function takes 3 arguments. It concatenates this, this, and this. This function takes 2 arguments. Argument 1 is this outside wrapper. Argument 2 is this inside operand, or whatever you would call it. But how would you apply that to a system outside of Chinese? So the approach that I use to describe the system is as follows. First of all, the assertion is all graphemes can be represented as headed trees, and I'll explain what that means, of predefined shapes and concatenations. Do you believe that? That's a big assertion. You should not believe that. Let me try to convince you over the next 20, 15 odd minutes that what I'm saying is possible. No, and the second assertion is no 2 distinct graphemes are represented by the same annotation. So there's an injective mapping, essentially. So that if you have capital O, lowercase o, and 0, those are all visually distinct. A speaker can identify the differences between them. They should all be represented with different annotations. But the converse is not necessarily true. 2 different annotations could represent the same grapheme as 2 different possible interpretations. So it's not necessarily a bijective mapping. That asterisk on all graphemes. Some graphemes are not well suited to be represented. So I've tried this with Egyptian hieroglyphs, Mayan, Rongo. It doesn't seem to work out. Whereas Hanzi, cuneiform, linear B in the script, these seem to be more workable. So there seems to be some dividing line. So first is a grapheme can be represented as a combination of shapes and operations, where each concatenative operation takes in 2 shapes as an argument. So let's start with what inventory of shapes could make this work. Let's start with a basic set of shapes which we can extend later. So you have your horizontal line, you have your vertical line, and then you can form more complex shapes with this. So we arrange it into rows. For the sake of just being able to talk about them, we can call this the second row the R series, the C series, the O series, S series, and E series, just for naming sake. Why not fewer? Why not just have the horizontal line and the vertical line? That can explain everything else, right? The problem is when you go to actual annotation, it seems very difficult to work with such a restricted set of graphemes. So this may make sense later, but if you have capital A, you have a diagonal line this way, diagonal line that way, and a horizontal line this way. So A is concatenating with B is concatenating with C, and A is concatenating with C. It's a triangular concatenation. That is impossible actually to describe with the system that I'm going to set forth today. So you need to represent this, the hat of the capital A as a singular shape that is concatenating with the horizontal line. So the long story short of why not fewer shapes is the system doesn't work with fewer shapes. So let's augment this inventory. You have this orthogonal shapes, but it doesn't really work if you just have orthogonal shapes. A lot of writing systems have curved shapes and diagonal shapes. So I'm proposing to you that most of these orthogonal shapes have a similar shape in a different subspace. So a curve, there's an equivalent curved shape and equivalent diagonal shape. So work with me here. I'm saying that here are the set of all shapes that we'll use, and you can use this to express most graphemes in most writing systems. I introduced the blank, the null shape there, because it's always good to have a null in linguistics and a dot. So for lowercase I, you have a dot and not any other shape there. So because we want to represent this on the keyboard, you have some equivalents here. So this backward C-looking shape is called the A shape. The blank shape or the null shape is the B shape, the C shape, and so on, right? So we have our inventory of shapes. Now we want to modulate them because you have capital O and lowercase o. It's the same shape. How do you distinguish between the two of those? And you have size modifiers for that. So there's 4 size modifiers and for height and 4 for width. Why not fewer? Because the system doesn't work with fewer. That is to say that there are some writing systems that distinguish between an B and an M or an M and an S. So small, medium, big, huge. That's how you remember those. So small is, imagine that there is the baseline, the medium, and the cap height. Now, not all writing systems necessarily might accord to this typography, but I submit that it's a useful abstraction to have in the back of your mind. So for the lowercase x, you have it extending from the baseline to the medium. This we define as the M height. It's medium in height. Baseline to cap height is B. Anything smaller than a M is an S, and anything larger than B is an H. H we need for Hebrew writing systems because some of them extend further. And then the equivalent on width is I, A, U, and O. So here's some examples of an indentation. So capital O, you have a tall shape, B. It's pretty wide. It's about as wide as it is tall. That's U. It is an O of the curved subspace. So height, width, subspace, and the basic shape being used. Lowercase o, you just change the size, the height and the width, but you preserve the shape being used. And then you have an omega and a capital lambda. This is just cute at this point. This is not very much is going on here. It's just, okay, you can annotate it in this way. What becomes more complex is when you have more shapes. You have multiple shapes being concatenated together to form a grapheme. So when you concatenate, you need to know where you're concatenating. That's where this comes in. So B versus D, it's the same shapes being concatenated, the same concatenation type. We are going to discuss concatenation types in the next slide. But the place of concatenation is different. So how do you resolve this? This is something that I bashed my head on for a long time. For each shape, we project a 5x5 coordinate system, such that if you say, I want to concatenate onto the top left, that is the 1, 1 coordinate, the bottom right is the 5, 5 coordinate, and so forth. So that's how you do that. In the next slide, I have some examples. Hopefully, it'll make more sense there. So you have 4 different concatenation types. Let's go through each of them. First is just the basic concatenation. This is like in MS Paint, if you were to take this shape and then take this shape and put it together, this is how it would look. So the grapheme for N is an N shape plus a vertical line. That would be MACN at this concatenation point plus at this concatenation point MITL. Same for capital P. You have something like that. You have a floating concatenation, which is this percentage sign. So for I or for Xi, you have shapes that are concatenating together, but that are not on top of each other. That's how you would represent those. You have the approximation concatenation and the replacement. So these are, if you want to say that this method of representation doesn't hold mustard, here's where you would sort of critique it, because these are a little shakier, but let me try to explain it. So sometimes you have, such as in the eta, this, that's the wrong transcription for it, I apologize. Eta, you have a vertical line, and then you have an N shape that is extending straight down. That extension is a fluid motion. You would not represent an N shape in this weird way, and then in a sort of jagged, discontinuous way have a line down. So it's a fluid motion. You would represent that as a vertical line and then an N shape and another vertical line. And then the replacement concatenation essentially takes part of a shape and replaces it with another shape. So you take this right side of this big N shape and you replace it with this three-looking shape, which is called the K shape. So this becomes necessary in order to explain certain behaviors in especially Telugu and Malayalam, certain Indic writing systems, but it's used in other writing systems as well. When I talked about this with my undergraduate advisor, and she called this a butt shape, but she always didn't laugh after that. But those are the four concatenation types. And the second principle is that when you're doing concatenations, it is underlyingly a binary tree structure. So when you're adding numbers together, for instance, 5 plus 2 times 5 plus 3, you're taking these two operations. Then to the result of that, you're multiplying this other 5. And then to the result of that, you're adding this. And a similar principle is going on here, that when you're concatenating multiple shapes at a time, you're concatenating 2 at a time, 2 at a time, 2 at a time, and the underlying structure behind this can be represented as a tree structure. The problem is when you have multiple shapes concatenating at a time, it becomes hard to disambiguate what is concatenating with what. So when we're concatenating multiple shapes, how do we know what concatenates with what? This is the slide when I was preparing the slide deck that I was like, I'm going to lose people on this. It's because it's a hot day, and there's the tree-headedness was for me difficult to figure out. I was inspired by the HBSG grammar in semantics, which also uses headed inheritance structures to disambiguate certain information. So when you're doing A plus B plus C, if you're concatenating two shapes together and to the result of that concatenating a third shape, how do you know which concatenates with which? So does C concatenate onto A or B? We need some way of disambiguating this with some rule. So one thing we can't have, which we had in the previous slide for additions and math operations, is when you do 5 plus 2 times 5, you're resolving the internal thing first. You're adding 5 plus 2 equals 7, and then you can do 7 times 5. Here, you can't, there's not a result. A plus B doesn't resolve into D. It's just A plus B. So that solution that's there in math is not there in this. So when you're concatenating onto a composite of multiple shapes, you're concatenating actually only onto one of its units at a time. And to disambiguate which one, we need tree-headedness. So you have a subtree concatenation, so a concatenation between two subtrees like A and B and C. I have, very thankfully, a whiteboard certain thing here. So A and B, and then C, concatenating like this. When you have a subtree here and a subtree here, the concatenation between this subtree and this subtree is described like this. The head shape of the left subtree and the head shape of the right subtree concatenate together, and the head shape of the tree is the head shape of its left daughter branch. If that is ambiguous, I'd be happy to explain it later as well. This head shape principle is very important because the question is, how do you know what order to write shapes in? If you have the, P or B or something, is it a line and then a circle, or a circle and then a line? The head shape principle, in many cases, establishes that one need go before the other. And so it reduces the number of equally valid annotations there are. Now, there's a question that you might have, which is how do you represent this displacement on the baseline using the system? So if you have lowercase p, you can't just have the baseline like this and then have a lowercase p like that. It has to go here. So sorry for the people here. Yeah, I just do the share. So the way that we mark the displacement of P, G, Q, etc., without needing any additional notation, is that we add a implicit rule, which is that the head shape of a grapheme rests upon the baseline naturally. So if we have that rule, we don't need to add any explicit marking of this displacement. It arises as a natural result. So if we define our head shape property properly, this displacement is an emergent property that arises. So at this point, hopefully I bought you, but maybe you're still very skeptical about, does this system actually work? Can it describe the things it's claiming to describe? Consider annotating your own example. So I'm going to go through an example annotation of a grapheme and see what annotation or grapheme you have on your own name tag. It's very serendipitous that this exists, and it's in Noto Sans, which is the font that I used for my own annotations because it is sans serif. And for scripts which usually come with stroke width variation, like in Hebrew, it does none of that, which makes it very easy to analyze with the system because stroke width is something that it cannot handle. It pretends like everything is zero dimensional. We'll take this grapheme, which is in Malayalam, and see how does it go from a grapheme to an annotation. So there's a lot of components into it. We need to break it down into subcomponents, break those subcomponents down until we say, this is a basic shape. This shape is within our inventory and thus is describable. So this is how we do it. We take this grapheme and we divide it into two subgraphemes. What is interesting, what can be motivated by this analysis is that these two subgraphemes are actually graphemes in their own right within the system. So this was actually what inspired me to do this whole thing in the first place, which is there are seemingly very complex graphemes in certain writing systems. This is the first letter of the writing system Malayalam, and it's so complex. How does a person represent all of that complexity in their head? And although I very carefully avoided psycholinguistics in this analysis, in this annotational system, maybe it is that they are able to represent it as an abstraction that says you take this subcomponent and this subcomponent and you combine them to create this. That is very speculative. So if you say that doesn't make any sense, that's reasonable. But you take this grapheme. I have excluded the orientation operators here just for visual simplicity. And then you use this ampersand concatenation, this approximating concatenation to combine the two. You take that scranked or butt shape, as my advisor would call it, and you decompose that into this big N shape and this 3 shape or the K shape. On the right side, you take this M-looking shape. There are multiple possible analyses. If we saw a version of an attested form of Malayalam, which did this, so it stopped short of the baseline, that could be an M shape in the decomposition there. But the question of what is the proper analysis, what is the proper annotation, is something that really is a case-by-case basis because it could vary. But you take this M-looking shape and you decompose it into N shapes, and then you take that N plus O shape and you decompose it into N plus O. So we have this decomposition, visual decomposition. Then you write it out as the basic shapes and operations. So it's this tree structure that is represented as a string. And then you write out this whole complex jumble of characters. And the assertion is that everything that is going on with the grapheme can be represented using this string, which then represents a tree, which then represents the grapheme itself. So I can explain it depending on how much time we have, but you can write this out as a sentence. which is that you say you create this curved end shape of this size, this height, and this width, and then to the 5, 3 coordinate, which is to the right middle of that shape, you do this replacement concatenation of this K shape of this such and such size, and then to the whole thing, which is to say to the head shape, which is this, to the 5, 5 coordinate of the head shape of that, you do this approximation concatenation with the 1, 5 coordinate of the head shape of, et cetera, et cetera, et cetera. So it's a complex thing being represented in what I assert is the simplest way it can be. What if we want to go the other way? What if we want to say, here's an annotation, here's the grapheme, which is what this system claims to do. This should be able to be transcribed as a certain grapheme. So we take this annotation and we write it as a tree, which we say is what it is underlyingly. Then once we write it as a tree, you replace the elements of the tree with the shapes that it claims to represent. So this BUCD looks like that. This BUCU looks like that. MUCO looks like that. And then we go from there. Now, once you have this, hopefully you can try this yourself. How would you concatenate this shape at that point with that shape at this point? It would result in this, which is also Malayalam grapheme, if you're curious about the origin of it. Why do we care about any of this? We claim to have a system by which these two linguists can survive their ordeal. They both live. Very good. But why does this matter? Does this actually capture something that is interesting to researchers? It's interesting as a puzzle to me, but can we create interesting behavior from it? If we have a working abstractive model, and if the system that I have described of going from a grapheme to a tree is indeed a working abstractive model, we can answer some good questions with it. How complex are graphemes from various writing systems on average? We can create a measure of graphemic complexity that arises naturally from this system. Does complexity correlate with writing system inventory size, as previous analyses have indeed asserted? Can we produce a metric of graphemic similarity by saying there are tree similarity functions that mathematicians use all the time? Is there some measure of that we can extend to this system? Which writing systems have the most easily confusable graphemes? If we have a measure of graphemic similarity, we can say very similar graphemes are more likely to be confused. Therefore, is there a most similar writing system and a least similar writing system? Which writing systems are not representable by the system, and why? Do we need to expand our annotative inventory or constrict it further? Is this the right inventory? Those 4 concatenation types that I've told you about, do you believe in all of them? Or do you think that 1 or 2 of them are suspect in nature? Since this is a generative grammar, as I said, so you can actually represent this as a formal grammar where you can generate all the possible shapes and then generate possible concatenation types from these shapes. If that is true, then there's a state space of all possible graphemes that exist that can be represented by such a grammar. Can we generate new graphemes then? If you say, I want to create a new letter for the Roman alphabet, and I want a computer to be able to generate 20 different options for that. Is that something that you can do? What about context-dependent writing systems such as Arabic and Manchu? Because you can represent individual graphemes, but as soon as they concatenate with one another, right now we're not handling that. We're just saying there's grapheme 1, grapheme 2, grapheme 3, and they're disjunct. But what if they're not? That's not something that can be handled by the system currently, but you can expand upon it. How does this figure into pandemonium architecture? So I coded a lot of this in Python, and I coded a version of pandemonium architecture, which essentially takes in a string input and then compares it with all known graphemes and says, what is the most similar grapheme? So what is the most likely grapheme that this representation will be? So those are all questions that you can answer if indeed this is a working abstractive model, which is a big claim. So we can do a few things. I don't have much time, and that last example didn't render, but that's fine. Certain graphemes, you could say one is more complex than the other, one is less complex than the other. If it's strictly additive, it's very easy. you say, I'm adding more shapes onto this original grapheme, so the one which you've added more shapes on is more complex. And that is Malayalam. I and J, I don't remember what those graphemes are. And then square and square, which is not the original representation, but those I would say are equally complex. When the relationship between two graphemes is additive, scoring complexity is less challenging. What about when it's not so straightforward? What do you do in this case, left or right, which is more complex? Of course, the model that you would use is you would ask speakers or writers and say, please evaluate which is more complex than the other. And we have a lot of data on that. But if we want to ask a computer, what is more complex than the other? You might want to, you could use parametric complexity, you could use the grapheme as image models, but you could also use something like this. So many possible complexity formulae we could use that arise from this tree annotation. One in this analysis, and I'll wrap up right after that, is saying there's a weighted score. You don't have to believe in this as an accurate model of complexity. You should question it. But you say if the shape is null, there's no complexity being added. If the shape is this E series or the S series that I mentioned at the beginning, you add 2 complexity. Otherwise, you just add 1 complexity for every shape. And then you say the complexity for this shape is, or this grapheme is such and such and such based off the tally. So we annotate 8 writing systems, 10 if you separate Roman and Greek into uppercase and lowercase sets, which I found was important to do. And then say, is there a correlation between the size of a writing system and its average complexity, which is a problem that's been done before. We would expect a trend line that goes up as the size of a writing system increases. So here's the results in a statistical measure, but what I think you would want to see is a graph. That's a very nice looking graph. I added also numerals for this just for my personal interest. So Malayalam numerals are more complex than other numeral systems. But Telugu is off the charts. It's much more complex than you would expect. And that's because a lot of graphemes in Telugu have this checkmark looking subcomponent, which checkmark is, diagonal, which adds 2 complexity to a lot of the graphemes, which shoots up the complexity on average. But in general, this is, to me at least, a very pleasing result. What you would expect, the behavior that you would expect to come out of it emerges from this system. I don't think we have time to talk about similarity, but thank you so much. And I'm open to any questions.
I'll find the way to keep 2 questions.
Yeah, thanks.
But I have a double question.
Oh.
Is that seeing your notation, I have the impression that you are reinventing functional programming. And you are asking yourself what level of detail and granularity should I have? And if you use a programming language, then this question is irrelevant because you can use any level and also have abstractions at any level. And you don't need tree structures because you assume that there is a tree structure, but this is something really artificial because of XML, because of Lisp, because of many historical reasons. But in real life, not everything is a tree structure. So this is my first remark. And the second, more important remark is that you are assuming that in the images you have shown that all strokes are uniform. So you are completely forgetting the instrument used traditionally for those writing systems. And for example, in Japanese, writing order is important.
Yes.
Because of the order, strokes are drawn in different directions. And this is not something you can easily model with this level of abstraction because it's always, you can always consider it as a diagonal, but a diagonal drawn this way and a diagonal drawn that way are completely different things. And you need, for that case, a level of detail which is much higher than for other graphemes of the same writing system. So somehow you should also introduce the instrument.
Yes. I don't have a, thank you for your comments. I don't have a way to introduce the instrument, but the distinguishing a grapheme that goes up to down can be done by introducing an additional variable as an adjective. So instead of just size and the subspace, as I called it. You could also introduce like P versus Q, and P says this is the shape such that it is written in this writing direction versus this writing direction. And so you would essentially double the inventory that was introduced in that original slide by saying there's an additional variable.
It should be visible. It's not only a parameter, theoretical parameter to
Mhm.
add it to your database, it should be visible by your stores.
Mhm. Yes, it would be visible. So you would essentially say, yes, so it would be something, sorry for my, this thing, but you would have something like this, as two different, shapes within the, system. What would not be, represented, and something you might consider important, is, this, tree structure does not, claim that the order in which the shapes appear in the tree is the order in which they will be written out. So if that is, it is claiming that it exists a priori as a perfect image, which is a simplifying assumption which you may completely disagree with. So it does not encode the actual way that speakers approach or writers approach writing out the grapheme. If there's any other questions, I would be happy to.
We can keep the conversation.
Yes.
Your meeting person. We need to go forward.
Thank you so
Yeah,
much.
thank you so much. Yeah.